There's one more thing I'll ask you to do, but fortunately that is really easy. So we now do have this robot, and the robot's coordinate system is like this. And as I told you earlier, the beams go like that, and back here is an area where no measurements are returned. And now what you just computed is the ray indices that point to the cylinders in the scene and the range. Now this here starts at index 0 and it ends at index 659. So this may be index 400. I want you now to produce the XY coordinates in the robot's coordinate system. So for every detected cylinder given a ray index and range, I want you to produce the X and Y in the robot's coordinate system. And for converting the ray index to an angle, there's a function provided in the LegoLogFile class, which is called LegoLogFile.beamIndexToAngle. And this will convert the index, like 400 here, to an angle measured in radians. There's one modification that you'll have to apply to the range measurement. Remember, the robot measures some cylinder. So these are the rays. And from that you would expect a range measurement, which looks like that. This should be this ray. And then these other rays, they are closer. So it should look somehow like this. But as you probably noticed, in reality, the outcome of our LiDAR is something like that, even with a peak in here. And in our algorithm, we just computed the average of all those values, which then is here. So in that case, we may get something like that. But as it turns out, this is the correct value for the cylinder's distance. So the cylinder is here, and we would have to apply an offset of the cylinder radius, which is 55 millimeters. But in addition, we have to apply a correction here. Empirically, I determined that this correction that we have to apply may be something like 90 millimeters. And so whenever you convert one of your resulting ranges to the XY coordinates, remember that you get something like this range, and before converting it to XY, you will have to add up 90 millimeters. And this is called the cylinder offset. So, and this is the final modification I'll ask you for. The program is find cylinders Cartesian, and it consists of the compute derivative, which you know already, the find cylinders, which you'll just have to fill in from your previous solution, and this new function, which you'll have to program. So this function gets a list of all the cylinders that were detected in one scan. This might be 0 or more cylinders, and then for every cylinder it takes the total beam index range and from that has to compute an XY coordinate. And just for now I have put 0, 0 here. And now let's have a look at the main function, which I modified a little bit. So there's still the minimum valid distance and the depth jump, and there's now the cylinder offset, which is a global variable which you may use in here in the function you have to program. It still opens the log file and reads the log file, but now instead of drawing the result, it will produce a file called cylinders.txt, and it will write for every single scan one line to this file, which starts with DC, meaning detected cylinders, and will then list all the Cartesian coordinates of the cylinders you've just found. So in the loop, it calls the computation of the derivative, it calls the find cylinders, and then it calls your new function compute Cartesian coordinates.